Thank you for the introductions. So today I'm going to, as I said, I'm currently working for COWI as an assistant engineering geologist, but today I'm going to talk to you about the research I did from a PhD at the University of Strathclyde over the past 4 years. So the title of tonight's talk is Core Surprise, What's Inside a Plate Boundary Fault in Scotland. This research, for those who are interested, has been published. So it's been published in a Journal of the Geological Society paper just this year as a paper in Earth and Planetary Science Letters, and last year it was the feature article in this Geoscientist magazine. So why are plate boundary faults important? Major earthquakes can occur on any large fault, but 90% of earthquakes are associated with plate boundary faults. Therefore, understanding the structure, for example, the fault core composition, the thickness and the geometry of large faults is crucial because their fault structures and properties control how and where earthquakes rupture, nucleate and propagate. And this in turn limits the size of the earthquake or the amount of radiated seismic energy and consequently the surface severity and damage. So for example, the 1999 magnitude 7.7 earthquake along the Chulungpu plate boundary fault, which was the second deadliest earthquake in Taiwan's history, saw significant variation in slip and ground motion at different locations along this fault. Which is shown in this image. So as you can see, the damage from this earthquake ranged from burst dams to collapsed buildings, bent running tracks, etc. And the northern end of this plate boundary saw the highest fault displacement and consequently the greatest surface severity and damage, but the southern end had small displacement, therefore the surface damage at the southern end of the fault was minimum compared to at the northern end. So subsequent field investigations related these changes to variations in the fault structure. For example, the width of the clay zone in the fault core or the geometry of the fault, which in turn controlled how the fault moved. Therefore, it is important to understand the internal structure of large plate boundary faults if we are to better understand and mitigate damage from future events. So to give you a little bit of background about faults for those who have never worked with them. So faults are not just a line on a map as it's commonly shown. It's actually an interpreted 3D seismic volume. It's a zone of variable deformed fault rock that forms through complex interactions between mechanical, chemical processes, etc. So studies of the internal structure of a fault typically splits it into 3 components. So you've got the host rock, which is the type of rock being faulted. You've got the fault core, which is in the middle, and this is the zone that accommodates the maximum displacement. And then you've got, around about the fault core, you've got the bounding damage zone, which is highly fractured and has small scale folding and veins. And the key distinction is that the damage zone does not display any shear where the fault core does. Like I said, 90% of global seismicity occurs on plate boundary fault, but despite this, our knowledge of the internal structure of plate boundary faults is actually lacking, as opportunities to directly study large faults in terms of both length and displacement is limited because field studies are essentially biased towards features that humans can realistically observe and measure. So it's a lot easier to measure a fault in the field that has small displacements because you can actually see the displacement. So for example, as shown in this bottom figure, it's a compilation of data from multiple fault studies that show faults generally get wider on average with increasing total displacement, albeit with a large range in magnitude of width for a given displacement. But this displacement thickness scaling relationship represents a growth, where low displacement faults represent a stage of early growth, and they're narrow, but as the fault grows, the fault zone evolves into a wider and more complex zone with increasing displacement. And this is, I've tried to show this in the schematics on the top. So in A, the fault is in its early stage of growth with a simple geometry, but as displacement increases, as shown in B, the fault geometry becomes more complex, and you can get fault lenses, for example, large lenses broken off the host rock. But the vast majority of data in that compilation comes from intraplate faults, so it's the faults within the interior of the tectonic plates and not the boundaries. For reasons that I've mentioned, basically because they're difficult to study, plate boundary faults have largely been excluded from this data set. But recently there have been several drilling projects undertaken to explore how the internal structure of active plate boundary faults at depth influence how they slip. And findings from all of these projects, for example, in the San Andreas, the Alpine Fault, the Japan Trench, etc., they all highlight the presence and importance of clay-rich fault rocks within the core. So this slide shows the Seyfod borehole that was drilled through the San Andreas plate boundary fault. And drilling at this location revealed that the internal structure of the San Andreas fault consists of wall rock of contrast and lithology and of distinct terrains. So on one side you've got quartz feldspathic rich crustal wall rock, and on the other side you've got oceanic serpentinite wall rock. And in the middle you've got this fault core that consists of a foliated gouge with serpentinite clasts within it. Such projects, though, are expensive. So the bill for the San Andreas fault alone was $25 million. And they are also limited in what they can tell us, effectively only spatially, they're spatially limited, effectively only capturing a 1-day transect along the fault. And it doesn't allow us to capture the variability in the internal structure at different locations. So, all that said, what about the internal structure of an ancient plate boundary fault in Scotland? This is a picture of the Highland Boundary Fault going through Craigieven Bay in Stonehaven. And the Highland Boundary Fault, as many of you may be aware, has been the subject of many studies of regional tectonics. Comparable to the San Andreas fault, the fault separates two distinct terrains. So on one side you've got quartz feldspathic crustal wall rocks that belong to the Dalradian supergroup, and on the other side you've got oceanic serpentinites. But unlike the San Andreas, this is actually a relatively well exposed along strike section of the fault. As I said, the Highland Boundary Fault has been studied by geologists for over 100 years in terms of its regional importance, but nobody has looked at the internal structure. So with permission from the Scottish Natural Heritage and the associated landowners at the site, we went to the beach and dug it up. So I don't know how many of you are aware about the Highland Boundary Fault, so just to give a bit of context, the Highland Boundary Fault is a mature crustal fault with a very long and complex history. In the present day extends from over 240 kilometres from Stonehaven in the northeast of Scotland, all the way down through Loch Lomond, the Isle of Bute, the Isle of Arran, and then possible along strike extensions into Ireland. It separates the Grampian Highlands from the Midland Valley. So if you're ever driving up the A9 and you go from the low-lying flatland of the Midland Valley and you suddenly get into the hills, you know you've crossed the Highland Boundary Fault somewhere. So these images, that's the Highland Boundary Fault looking across from the top of Connick Hill at Loch Lomond, looking across Loch Lomond, and you can see it going through, marked by the islands. And again, this is the fault showing it's the best exposure actually across the whole of Scotland at Craigieven Bay. So, as I've already alluded to, the Highland Boundary Fault exposures at Stonehaven provide a really rare opportunity to study the internal fault structure of a major plate boundary fault. So first of all, I remapped the area and did 6 across fault transects known as structural logs to try and capture the variability at the different locations. So this is my map, and on the map you can see these rectangles with log 1, log 2 labels, etc. And those are the structural logs and the location of them. And just to reiterate, in this map, shown in the grey, to the north we have the Dalradian of the Grampian Highlands, and the south you've got the Stonehaven group and the highland border ophiolite, which is an assemblage of rocks that formed in the ocean crust, shown as the purple and orange. So the Highland boundary fault is thought to have been active during 2 events of the Caledonian orogeny. So the first event was the early Ordovician Grampian orogeny, about 480 to 460 million years ago, and then the Mid-Devonian Acadian orogeny, which was 420 to 390 million years ago. And like the San Andreas fault, the system has grown and evolved through time. So early motion was thought during the Grampian orogeny was thought to be reverse, and then it was reactivated in sinistral strike slip during the Acadian. But the magnitude of strike slip motion has been debated. So, and it wouldn't be surprising if there was other minor motions at a younger age associated with North Sea extension or North Atlantic opening, etc. So yeah, that's just again highlighting you've got the Dalradian at north, highland border ophiolite at this side of the fault, and then in the middle you've got this fault core. Again, this is just a picture but looking in the opposite direction to the southeast. So after digging and exposing the fault at these several different localities at the structural logs, I revealed a remarkable sequence of fault rocks through this ancient plate boundary. So at all localities, the fault core consists of a single high strain fault core bound on either sides by these damage zones of contrast and lithology, your crustal rocks and your oceanic rocks. So from south to north and in a cross fault transect, going from the bottom of this log, your highland boundary fault consists of a footwall damage zone that comprises of these various parts of the highland border ophiolite, a structurally and lithologically variable fault core, and then a hanging wall damage zone on the north, which has your Dalradian rocks. So just starting from the bottom of this log at the purple unit, I'll just go through and give you a bit more information on each of the units. So starting at the bottom in the ophiolite. So the first unit, that purple unit on the map, is a carbonated serpentinite that belongs to the ophiolite. And this displays a chaotic network of cross-cutting calcite veins. And it's cut by localised sub-horizontal fractures that have alteration halos. These fractures have an anastomose in conjugate geometry, comprised of curvy, cross-cutting, brittle cracks, and it's got calcitic alterations which extend approximately 3 centimetres either side of the fractures. And the alteration follows the same geometry as the fractures themselves. Next, moving up in the log, which was this orange unit on the map, you've got it's an intensely faulted and fractured buff-coloured, what we call a dolomitized serpentinite, which actually is properly termed ophicarbonate. So this unit formed from the alteration of serpentinite with a CO2-rich fluid in a process known as natural carbonation. Veins in this unit, as you can see in the picture, are 2 to 10 centimetres thick and are filled by multi-phase carbonate, including a very fine-grained massive dolomite in the middle, and then at either edges of the vein, lining the vein, you've got this sparry calcite. And the veins are aligned parallel to the highland boundary fault, but there are a separate set that cross-cut this and are slightly older. So this slide just shows you a section of these multi-phase veins. The calcite displays a dogtooth epitaxial texture indicating of crack seal growth and extensional opening mode fractures. So I'm not going to go into very much detail about how I made these stereo nets, but the field evidence from these veins suggests, as I said, there was two sets, one that was parallel to the highland boundary fault and a second that cross-cut that. So these veins suggest that there's been two phases of early dextral reverse motion on the fault. I also saw numerous small-scale sinistral and dextral strip faults arranged in radial shear geometries found within this ophiolite unit. I forgot to highlight that on the map in the previous slide. But so these radial shears are indicative of sinistral strike slip motion, but these faults offset these veins, so that it suggests that this the veining and reverse faulting that formed these veins happened before the strike slip faulting that forms all the radial shears, and which I'll come to in a minute, formed the fault core. So in order to constrain the isotopic composition and sources from which the carbonate in the highland border ophiolite grew, I did some preliminary measurements of delta 13C and delta 18O at the Scottish Cirque in East Kilbride. So the results show that delta 13C and delta 18O ranges across all, varies across all units. So the ophicarbonate and its associated multi-phase carbonate veins, shown on the image previously, have a signature of 0.1 to -3, indicative of a marine signature, whereas the carbonated Supentonite, that purple unit on the map, has a delta 13C of -5.5 to -8.5, indicative of a magmatic signature. So it indicates two different systems. But the delta 18O values are actually surprisingly fairly consistent, with a mean value of 19. So importantly, these delta 13C and delta 18O values are similar to those that have been reported for hydrothermal environments elsewhere. So one hypothesis is that the carbonates in the highland border ophiolite, these the ophicarbonate, the orange unit, and the carbonated Supentonite, the purple unit, are the result of hydrothermal alteration by seawater with the addition of this magmatic CO2 signature. I'm just going to skip this slide, but this was, you can basically indicate which temperature your fluids formed at using the delta 18O. So for the ophicarbonate, if you assume it's a marine fluid, you're looking at about 100 degrees C, and for the magmatic carbonated Supentonite, you're looking at a temperature of about 240. So all that indicates a hydrothermal environment. So now going on to the fault core. So by digging up all the large boulders on the beach, you can see that the fault core here actually consists of 4 distinct units that remain unmixed. So you've got a localized green gouge, which is just above where the person's pointing in the top left image, and then on the top right you've got a blue gouge of high plasticity. Bottom left, you've got this red foliated chaotic breccia, where the foliations wrap around centimetre scale clasts of the wall rock. And then on the bottom right, you've got this red crackle breccia, which has large elongated wall rock lenses. And you get localised pods of the red foliated chaotic breccia found within the blue clay, but overall they remain unmixed. So I'm just now going to go through and describe each of these units individually. And it just highlights that the units remain unmixed despite it being such a large offset fault. So starting with the green gouge. So the green gouge was very thin, about 30 centimetres thick, and it was only observed at one locality. So it could either represent a zone of localised alteration or a remnant fragment of a reworked previously extensive fault core lithology. The clay itself is relatively homogeneous. There are very, very, very small clasts, but that can only be visible under the microscope, and it consists of about 50% clay, 3 types of clay, elite, smectite and chlorite, and the rest being quartz and dolomite and anatase. This just shows the green gouge under the microscope. And I did some microstructural analysis, but I'm not going to go into all these. I've shown the numbers here, but I'm not going to go into them. All that you really need to take from this is that this green gouge has very, very small rounded clasts only visible under the microscope, and they're embedded in this green-brown fine-grained clay matrix. So next you have this blue gouge, which is of high plasticity, and it's exactly like modelling clay. So a member of our team actually managed to model a fish in the field out of this clay. It is internally foliated, with the foliations being subparallel to the highland boundary fault, and you've got small, less than 5 centimetres bleached white clasts, and occasionally you can get slightly larger ones. It has a very similar mineralogy to the green gouge, so it's roughly 50% clay with 3 types of clay, chlorite, elite, smectite again, the rest being quartz, dolomite and anatase. And I ran some permeability tests, and it's very impermeable clay. This shows some thin section images and my interpretation of these, and you can see that some clasts and matrix patches within the clay have a preferred orientation, which exhibit, well, obviously the strong fabric, but the fabric can deflect and wrap around the clasts. For instance, in the sample to the left, the clasts and fabrics are aligned typically 15 degrees anti-clockwise or 10 degrees clockwise from the principal slip plane in radial shear geometries. And again, to the sample from the right, the fabric is aligned at high angles, about 60 to 75 degrees anti-clockwise, and again in radial shear geometries. So there's obviously very clear evidence of shear here. You've also got strain shadows visible at different scales, and some open and mode veining or an extensional shear T-shears. So overall, very highly sheared gouge, and they're all aligned within these radial shear geometries in a sinistral-like strike-slip motion. This slide shows a selection of thin section images from this gouge at the multiple different locations along the fault, and typically the clasts are sub-rounded to rounded, so a preferred orientation is not always visible. A few clasts resemble what are known as clay clast aggregates, where you've got these like snowballed rims observed around rotated rounded clasts, and this fabric swirls around the clast, which you can see in the bottom left image. Some clasts have rounded edges suggestive of mechanical wear, whereas others are more tapered and elongate, suggesting shearing and chemical alteration. So again, I've presented the numbers of my analysis, but all take-home messages that these clasts are sub-rounded to rounded, spherical to elongate, embedded in a dark brown fine-grained clay matrix, and the clasts are getting slightly larger and less circular than the green gouge, which was closer to the main slip surface on the fault. And one of the main surprises, I suppose, was that within this blue gouge there was some marine microfossils, only found in very localised section. So if I just go back to the previous slide, so in this left image, so there's only a very, very small circle. I don't know if you can see my mouse actually, but in the top where the bump is on the slide, that's the size, the extent of the fossils. So the fossils themselves, you've got some bryozoans, possibly belonging to the extinct order the Fenestrata. You've also got some brachiopods and an echinoid spine. But importantly, as these Venustella are ancient fossils now extinct, they confirm that the clay is just not, it's not a modern day clay that's just been deposited on the beach. So it does have some implications for the mechanics and timing of it. In the presence of them, the fact that they still exist suggests that strain is localised, highly localised. But unfortunately, I haven't been able to complete any further work on these fossils. It wasn't really my area of expertise, so their presence and why they're there still remains somewhat a mystery. So moving further up, you get into this red foliated chaotic breccia, but the contact between the blue gouge and red foliated chaotic breccia, there's some alteration. So within the zones, there's pods of the red foliated chaotic breccia. From here on, I'll just refer them to red pods found within the blue gouge. And these pods have an elongate lens-shaped geometry. And again, the pods themselves are aligned within radial shear geometries. But this has some implications. The fact that you get the red clay within the blue clay has some implications on timing. So the red foliated chaotic breccia itself consists of sub-rounded to subangular, circular to elongate clasts embedded within this dark brown to red fine-grained clay matrix. The foliations, which are hematite, define a clear structural fabric, and the fabric itself is generally aligned parallel or subparallel to the highland boundary fault. But again, anastomoses wrap around these variably altered centimetre scale clasts, and the clasts themselves are of the Dalradian wall rock. So this clay has a slightly different mineralogy to the blue and green gouge that we saw, slightly less clay, and instead of, it still has 3 types of clay, but instead of illite smectite chlorite, which we saw in the green and blue, you've now got illite smectite and kaolinite. So again, this just shows a thin section in my interpretation of it. And again, you can see that the clasts in this clay have a preferred alignment, and that they're all within these radial shear geometries. But unlike the blue gouge, the clasts here don't display tails or strain shadows, suggesting that strain is not quite as high in this unit as you're moving further away from the principal slip planes. So again, here I've shown the numbers, but all we need to take from it is that the clasts are larger, more angular, less circular than the blue gouge. So the last of the 4 fault core units is this red crackle breccia, which consists of these large lenses of Dalradian wall rock up to 2.3 metres in length. Couldn't even get all one in the picture. And again, it wouldn't be surprising to hear that these clasts, these lenses, are aligned within radial shear geometries parallel to the highland boundary fault. So, as I've been going through all these fault core units, take-home message was that the clasts are becoming larger and more angular as you go away from the principal slip plane. So the clasts are present in every unit with sizes from sub-millimetre to centimetres, and they have a wide range of aspect ratios. So The smaller clasts, which you see in the green gouge, are more equidimensional, whereas the larger clasts have a wider range of aspect ratio. So in the green gouge, the clasts are small. In the blue gouge, the clasts are larger, have a wider range in aspect ratio, and then in the red foliated chaotic breccia, as you move further away still, the clasts are larger and have an even wider range of aspect ratio. This all suggests that the clasts have been plucked from the Dalradian wall rocks and that they've been preferentially attacked until this lozenge lens shape eventually diminishes to a more equidimensional grain through rolling, fracturing and or abrasion. I've given you a little bit of mineralogy as I've been going through. So the XRD reveals that the mineralogy is actually somewhat complex within this fault core, and that there was a distinct chemical change between the blue gouge and the red foliated chaotic breccia. So the blue gouge had illite, smectite and chlorite, which was magnesium and iron rich, whereas the red foliated chaotic breccia had potassium-rich illite, smectite and kaolinite. Therefore, it can be assumed that the blue gouge is chemically derived from the highland border ophiolite wall rocks, whereas the red foliated chaotic breccia has been derived from the Dalradian crustal quartz and feldspathic-rich wall rocks. As just said. Regardless of the lithology, 50% of the illite is of the 1ND polytype, which suggests that it's been fault derived, if you need any more evidence that these clays have been derived through faulting. So the last thing really to note about these fault core units is that not every unit is present at every locality along the fault. For instance, the green gouge is only observed at one locality, so could either represent a zone of a localised alteration or a remnant fragment of a previously extensive lithology. And similarly, the red crackle breccia is only observed at a couple of localities. So each unit is internally variable and varies in thickness along strike. So the total thickness of the fault core varies in this relatively short section of 500 metres, varies from 3 metres to 10.7 metres, which is a large variation over such a short distance. So in summary, I started off with the question, what's inside a plate boundary fault in Scotland? As I've just discussed, the answer is a structurally and lithologically variable fault core that ranges from 3 to 10 metres wide with these 4 distinct units. The green and blue gouge are derived from the highland border ophiolite, whereas the red foliated chaotic breccia has been derived from the Dalradian. But one of the most puzzling things for me was if these been derived from separate wall rocks, then why do you get these clasts, Dalradian clasts, showing this going from lenses to these small rounded clasts, Dalradian clasts within these units, implying that there has been a degree of so-called mixing, yet the units remain distinct. So I tried to put all these observations into some evolution model, and it suggests that the fault core units remain distinct as they formed at different stages of faulting and by different mechanisms. So looking at the top square and working down, I'll just talk through it. So early in the fault's history, the Highland boundary fault have juxtaposed the carbonated Supentonite, which was that purple unit, and the Dalradian wall rocks. So the carbonated Supentonite here would be mechanically weaker than the Dalradian, so the fault would have made use of this weaker unit. So through natural carbonation, you have fluids coming up and it's altered this carbonated Supentonite into the ophicarbonate, which was that orange unit. And this was associated with, as you saw with the veins, with an early dextral reverse motion, which enabled CO2-rich fluids to come up or along the fault, dolomitizing the Supentonite and forming these multi-phase parallel fault parallel veins. Going down the model, as I said, the dextral motion is early, and then you move on to this sinistral strike slip motion later. So the first stage of that sinistral strike slip motion, you've got your ophicarbonate deformed by with radial shear geometries at different scales, which is evident from the field map and from the orientation of the microstructures in the thin section images. So again, moving down, after the alteration of the carbonated serpentinite to the ophicarbonate orange unit, the mechanical strength contrast between the two wall rocks will have changed. So the Dalradian would have now been weaker than the ophicarbonate. So at this point, the fault's going to brittly deform the weaker Dalradian side through grain size reduction and plucking off these lenses. So the fault, again, the mineralogy in the fault was fault derived. It's a mixture of fault derived and orthogenic, so suggesting part of it's been derived from the wall rock and parts been altered through faulting. So that's pretty convincing evidence to me that this red foliated chaotic breccia has been derived from the wall rock of the Dalradian, plucking and breakdown, and then altered through this sinistral strike slip faulting. And shown that the Dalradian class size and roundness spans the entire range from this lozenge shaped to subangular to subrounded to subequant class in the blue gouge, and finally to the small rounded circular class in the green gouge. So the class therefore becomes smaller and more equidimensional towards the principal slip plane, suggesting that the Dalradian continually becomes incorporated into the fault zone. And this process of the class becoming incorporated into the fault zone, plucking off the walls, is not unique to the Highland boundary fault and occurs in many fault zones across the world. So next stage, again, there would have been a flip in the reversal. The strength contrast. At this point, you start processing your ophicarbonate wall rocks. And I propose that this occurs over 3 stages, similar to what's been described in literature for the San Andreas. So first you get this injection of fluids along the radial shears. Then you get clays forming on the shear fractures, so the blue gouge starts forming from the chemical alteration of the ophicarbonate and carbonated serpentinite units. And the clay growth and fabric have been controlled by the radial shears in the fault. And then you get this clay fabric development. So once most of the serpentinite is broken down into the blue or green gouge, slip was accommodated by ductile flow along the clay fabric, resulting in the foliations wrapping around the pre-existing class of the Dalradian wall rock that have previously been incorporated into the fault zone. And these clasts during this point were reworked and sheared into the strike slip geometries, and you get your strange shadows and your wings as you saw in the thin sections. And the last stage of the model is after your formation of this blue gouge from the chemical alteration of your ophiolite wall rocks. The fault would have underwent episodic widening, and you just got some more clasts coming off the wall rock, forming these red pods. So they're actually known as rip-out clasts. So for when there was a reason for the fault to wide, the fault plucked off the bits of the clasts. They're still in radial shear geometries, and the fact that the red pods are found within the blue gouge and not the other way around suggests that the red foliated chaotic breccia is older than the blue gouge. So this model just gives a scenario explaining why this large offset plate boundary fault consists of these distinct fault core units that remain unmixed. The red foliated chaotic breccia formed first from the Dalradian, and later you've got this blue and green potentially gouge forming later due to the alteration of the Supentonite wall rocks along the shear fractures. But in order to confirm any of this model, you really need to date both clays, and actually the samples as we speak are currently at CSIRO in Australia, waiting to undergo some argon dating. So the last question remains, well, how similar, why does this matter? How similar is this highland boundary fault to other plate boundary faults we see? So if you can remember back to the very beginning of the talk, I said that faults get wider on average with increasing displacement, and it represents a growth trend. However, the vast majority of the faults in that data set that showed were from intraplate faults and not plate boundaries. So in order to determine how similar the highland boundary fault is to these other plate boundaries, I compiled all the data I could on the fault core thickness, and only included studies where the width and composition of the fault core are clearly defined and reported as being distinct from the damage zone. So this is my compilation of data, and it shows that the intraplate faults, they do get wider on average with the fault core width, does get wider on average as the fault gets bigger. And on this trend line, plate boundary faults have very large displacement, so you'd expect the fault cores to be very wide. But as I've shown in the highland boundary fault, it can be as narrow as 3 meters. So plate boundary faults actually don't fit this trend. So this is the data collected from all plate boundary faults that I could, and they all are anomalously narrow and don't follow this trend of increasing average fault core thickness with increasing displacement. So all plate boundary fault cores appear to be narrow, between 0.07 meters and 35 meters wide, with no trend. And in order to test whether this was related to their structure, I then constructed some schematic structural logs to show the internal structure of the highland boundary fault compared to these other plate boundaries. So in places, the highland boundary fault is similar to other plate boundaries. For instance, it's comparable, the red foliated chaotic breccia is comparable to the Seyfod clay that I showed at the beginning, in that it's composed of highly sheared foliated matrix that wraps around centimetre wall rock clasts that are parallel to the fault. But in comparison to all the data available, the fact that plate boundary faults cores appear to be narrow, looking at this, it doesn't appear to be related to the host rock, the plate boundary type, the way the fault moved, the number of fault core strands, etc. All these vary among plate boundaries, but plate boundaries all remain comparatively narrow, so we can only really say the highland boundary fault is comparable to other plate boundary faults in terms of fault core thickness. But this in itself has implications for how earthquakes behave. So for the purpose of time, I'm not going to go into much detail about how I made this figure again, but basically I compiled and compared the data between seismic moment, which is essentially a measure of earthquake magnitude, and average displacement for both plate boundary and interplate faults. And it shows that for a given value of average displacement, plate boundary earthquakes typically have a greater seismic moment and hence a greater magnitude than intraplate earth events, which is to be expected. The largest earthquakes occur at plate boundary faults. But looking at the seismic energy balance, the equation at the bottom, total energy during an earthquake is partly consumed by the fault, by fracturing the rock, creating a slip surface, and frictional energy, which is the energy required for this slip to occur on the new fracture surface. And this is represented by the EG and EF terms. And the remaining term ER is the amount of energy that is radiated to the surface as seismic waves. So therefore it is inferred that plate boundary faults, they're narrow, they have narrow fault cores, so for this reason they're not going to process intact rock as much as intraplate faults during seismic events. Therefore, the fault themselves is going to consume less energy the fault's narrow, whereas interplate faults are wider, they're going to consume more energy. So the less energy consumed in EF and EG, the more can be radiated to the surface as ER. So plate boundary faults, you're going to consume less energy, you don't need to have these wide fault cores, and you can radiate more to the surface. By contrast, interplate faults, they're going to consume more energy, generating these wide fault zones with complex geometries. And the more complex geometry, the more energy has to be consumed at depth within the fault, therefore less energy reaches the surface. So in summary, because plate boundary faults are narrow, for this reason they don't consume as much energy as interplate faults during earthquakes, allowing more energy to be radiated to the surface, creating higher magnitude earthquakes. So basically, just to summarise everything, I know it's quite a lot of information, I've just provided a documentation of the structure of the highland boundary fault in its outcrop to microstructural scale, which is a valuable contribution to the global data set of plate boundary faults for which data is limited. So the highland boundary fault consists of these 4 distinct units that vary in thickness, and they remain distinct because of the differences in how the wall rocks have been processed. And lastly, that these fault core thicknesses that we observe at the highland boundary fault are comparable to other plate boundary faults. They all have narrow fault cores, which has implications for the earthquake energy balance and understanding how earthquakes behave and dissipate this seismic energy. So this is just a list of references. So thank you for listening. Just be welcome to answer any questions.
Lucy, this is Phil Mollicone. Thank you very much. That's a very interesting talk. Are there any questions? You can either type them, raise your hand, and we can unmute you, and you can ask Lucy yourself, or type them in and I'll forward those on. Right, we have one from Peter Robotham. What evidence do you have that the highland boundary fault displacement is 30 to 150 kilometers? I'm glad Peter asked that, because I was going to ask the same thing.
It's basically from the literature.
Is there any way to tell by the local magnitude and amount of deformation and rock processing?
Oh, I don't know, to be honest. I don't know, no.
Okay, that's
Sorry.
fine. Right, and I thought of a question. One of the last slides, you had several plate boundary faults diagrammed. Among those, how many are San Andreas type, almost pure wrench, and how many are sort of thrust, orthogonal thrust?
So there was about total. I think I had 13 different plate boundary faults in total, and I think 10 of them approximately were strike slip, and about 3 were thrust.
Okay, so a reasonable mix.
Yeah.
Yep.
More strike slip than thrust.
Yeah.
For obvious reasons, that they're easier to study at the surface.
I wonder if there's any idea what the population of strike slip versus thrusts overall globally would be.
Yeah.
Yeah.
I think strike slip would be
dominant.
Yeah, because it's on the surface essentially, really, isn't it? Like the displacement, you can see it on the surface rather than drilling a borehole down to see, unless you get a good section in 3D.
Okie doke. Simon Gould is asking, are there plans to extend this study to other outcrops along the fault inland towards, I'm missing the last bit of that, towards southwest?
Yeah, well, there was, during my PhD, that was a plan, but it never, I just spent too long analysing all this data at Stonehaven. So had I had time, yes, I would have, but I've finished the PhD now, so no, it won't
You could
happen.
always do a postdoc.
I could do. In an ideal world, yeah, I should extend it. I did at the very beginning of my PhD. I did go to other localities. So the Balmaha near, just on the shores of Loch Lomond.
Yep, that's the picture you showed, wasn't it?
Yeah, well, pretty much the same area, yeah, and in Ellen on near Dunoon on the peninsula.
Mhm.
But I couldn't see really at either of those. Like at Stonehaven through the bay, you can clearly see where the fault is. Whereas at those other localities, I couldn't even see where the highland boundary fault was, to be honest. There's some sketchy outcrops. You might be able to find some gouge if you dig, but you might be there a while because it's not so obvious where you should dig, if that makes sense.
Yeah. I remember going on a field trip to Balmaha, and there was a piece of serpentinite
Yeah,
at the surface, hidden in the woods,
yeah, I know the one you
that
mean.
must be
Yeah.
associated with the fault.
Yeah, so I think that's to do. I think there's a separate story, as I kind of mentioned in the talk about the serpentinite, so that's like hydrothermal stuff.
Mhm.
It must have been altered by the fault at some point, yes, but
Yeah.
I don't know where the fault is in relation to that, whether it was just a serpentinite mound or not, I don't know.
And Simon Gould has raised his hand. I will unmute him. Simon. Simon, are you there? Do you have another question? Possibly not. Let's see. David Casablanca is saying, thank you for a very interesting talk. And will you come back to tell us more about the fault zone paleontology, how these fossils got there?
I don't know any more about it, unfortunately. If I
But they're
find
old.
out, I will, but
I think you said they were Ordovician to Permian, so they're old.
yeah, yeah. Um, I don't know, to be honest. I really don't know how they got there.
Okay. Are there other questions?
Can I chip in verbally? So this is Peter Robotham. So I'm just wondering, why do we get such good exposure of the Highland Boundary Fault at Stonehaven compared to along the rest of it? Is it purely the surface conditions, or is there something different about the Highland Boundary Fault at this end of it compared to the further southwest?
Good question. So the Highland rhyophyllite exposures are not all the way along the fault. Well, at the present day, they might have been at one point. They might have been eroded out, but you only see these ophiolite exposures at certain places along the fault. One being Stonehaven. I think maybe like 5 places. The other being Balmaha that I've just mentioned. I don't know. I don't know why, to be honest. Possibly because of the wall rocks himself. That would be the most obvious one. But I'd need to really look. Because I think there's old red sandstone juxtaposing the fault at other places along it.
Mm-hmm. Okay.
I'm not sure. Sorry.
Okay.
Paul Mitchell has asked a question in the chat, and I think I might just try to unmute, but he's not unmuting. I was going to try and let him ask that question himself, but do you have any thoughts why plate boundary faults behave differently to the intraplate faults?
Because of their structure. As I said, they've got this narrower fault core. So I know because another reason I think is because the plate boundaries are already, if you think about plate boundary, plate tectonics, these continents, the boundary between the two plates already exists. So it's already a pre-existing structure, it's just got to slip. Whereas an intraplate fault that develops in the middle of these plates has to start as a crack and grow. So it's different mechanisms of how the fault originated, I think.
Okay. I was wondering if the Highland boundary fault is likely to extend seaward to the east into the North Sea. And you said that it extends westward, and maybe you can see it in Ireland. Is it likely that we would see the same kind of rock juxtaposition on the other side of the Atlantic in North America somewhere?
I don't think it extends that far.
Okay.
So, Phil, hopefully you can hear me.
Yep.
I was thinking it's 25 to 8, so we've gone a little bit over time now. So, if you have any questions, then now's the chance to ask. But if not, perhaps we should wrap up there and say a big thank you to Lucy for her talk, which was fascinating, very, very interesting. So, and I definitely feel like I know a lot more about my local area now, so that's great. So I'm very pleased to have listened to this talk. So yeah, thank you very much, Lucy. And thank you also to everybody who's attended this evening. I know the weather's not so good in Stonehaven this evening, so this was a good thing to do for sure.
Yeah, great. Thank you very much, Lucy.
You're welcome.
Yeah, thank you very much, Lucy. We really appreciate it.
No problem.
Thank you. Thank you. Bye-bye.
And good evening to everybody.